Yeah, as I was saying, my name is Mikel Irazabal, and I work in the MOSAIC5G team. And I am going to give you a brief tour of FlexRig E2 service models. So first, the outline for me today will be talking about the Oran E2 interface. It will follow the Oran E2 service models to explain a bit the background. Later, I will move to the E2 service models architecture in FlexRig, and I will finish with a summary. So let's start with the Oran E2 interface. So Oran E2 defines three entities. It defines the rig services, the application protocol procedures, and the information elements. The E2, there exist 4 rig services. They are named report, insert, control, and policy, and each service is composed of various E2AP procedures. There exist actually in the standard 26 E2AP procedures. 10 are messages for rig functional procedure, such as, for example, the rig subscription request. And there are 16 messages for global procedures, such as E2 setup request or rig service update. The standard also defines 32 information elements. So how does this look? So an ER rig may start a subscription to the E2 node, actually with an event trigger. And the E2 node may respond with an ACK, accepting this subscription. And when the event actually triggers, the E2 node will send a rig indication message to the rig. Now, how does this rig indication procedure, how it is implemented? So actually, this is from the standard, and we can see that the E2 rig indication message procedure, it is defined by many fields. Some of them are mandatory, some of them they are optional. And as we can see, for example, the rig request ID that we can see below, the rig request ID is formed by a rig requester ID and rig instance ID, both of them needing 16 bits to be represented. So in summary, the E2 interface is composed by rig services, procedures, and information elements. Services are composed by one or more procedures. Procedures are composed by many information elements, and the information elements actually they define the type and the valid ranges of the data. So let's move off how Oran defines the E2 services. So the definition of the E2 service model is the description of the services exposed by a specific run function within an E2 node over the E2 interface towards the rig. So it's from the run function towards the rig, and here it sits the E2 interface. The E2 interface is used to carry messages between a given run function and the rig, and these messages are run function specific. So this means that the procedure doesn't know the semantic of them. How does this look like, actually? Let's go again to this rig indication message procedure. And for example, we can see that one of the fields is the rig indication message, which is also mandatory. How does it look? Actually, we can see here below that information element type and reference, it's an octet string, which an octet string is another name for bytes, which actually this came back from the days where bytes were not defined as 8-bit creatures, which sounds strange nowadays, but it was like this at some point. And the semantic actually of how all this raw data is interpreted, this goes, or the E2 service model is the one that takes responsibility for understanding what they mean, to understand the semantic. There are 5 E2AP procedures that the service model should provide, and there are 9 information elements that the service model should also provide. And here it is the relationship from the standard. We can see on the right that there are these 5 are the rig subscription, rig indication, rig control, E2 setup, and rig service update. And in the left, we can see the 9 information elements: rig event trigger definition, action definition, indication header, and so on. So in summary, the service model, it exposes the information of a specific run function over the E2 interface towards the rig. E2 service model information is embedded within an E2AP procedure as raw bytes. So the semantic depends on the service model, as I just explained. And every service model provides the semantic to interpret this data. With such a design, E2 interface, it enables decoupling the protocol, this E2AP, from actually the data, the semantics, which is interpreted by the E2 service model. So with this in mind of the standard, let's see actually how FlexRig maps to this Oran E2 interface. So as Navid mentioned, FlexRig service models, they are designed as plugins. So they are shared dynamic libraries. They need to be loaded in the rig as well as in the agent. We need in both of them, and they have to match. And service models are built through the factory method pattern. So basically, the only way to create one service model is just make, in this case, this is an example of the PDCP service model in the agent. For them, the one that they are on the agent, we also need to give like the input and the output so that they can communicate with the run. With the run, in case of, for example, in a CU or a DU, they could also communicate with the 3GPP stack. So this is actually the code that one needs to add to, this is taken from OpenAirInterface to create the E2 agent. As you can see, basically you need to call the init agent API. You have to give a server IP address, basically. You have to give some information of the E2 node and the input output, that there are two functions, read run and write run. So the service models, they are able to read and to write directly on the run. And the only thing that we did change in the CMake list file of OpenAirInterface is adding just our statically compiled library libflexrig agent.a. We are very aware about the complexities that the OpenAirInterface has, and we are trying to tame the beast. We consider this very seriously. The FlexRig service model, it also has to provide 5 procedures. As you can see here, these are the procedures of the rig: on subscription, on indication, on control, on E2 setup, on rig service update. And they need to define also the information elements. Here, for example, we have an example of a PDCP indication message, how it looks like. So there is a length. We may have more than one bearer. And here we can get the statistics for every bearer. And they are done in C. And we use this as an intermediate representation, which I will explain now. The FlexRig service model, encoding and decoding, it can be decided at compile time. So we use static polymorphism. For that, we use a feature from C11, actually, it calls generic. So this allows us actually to have a 0 runtime cost overhead, and this it gives us the possibility of offering us great flexibility, since at compile time we decide which kind of encoding we want, and depending on the encoding that we want, different functions will be called. So if on the future we want to implement a new encoding or decoding scheme, this can be done very easily without changing any of the code that we are sure that it is already running. So let's go maybe to an example. So here are some basic blocks of the E2 agent and of the rig. So there is an asynchronous input-output, which is implemented as an epool. One can think of it as so. We have here an endpoint, which is an SCTP connection, according to Oran. Here we have the AP, which is an application protocol. It takes care of the encoding and decoding in ASN.1 as Oran actually defines, or we also did it with flat buffers. So at compile time, you can select actually which encoding and decoding scheme you want. Also, we can think of a message handler as another logical block. The service models that they are loaded dynamically as they are shared objects. And these service models, they communicate with the RAM through a read-write operation. And this message handler on the rig, it communicates with the IAPS. So maybe let's go to an example of how an indication message how it is the pipeline, so that we have an idea. So an event is generated, so a timeout arrives. An indication, it's normally a message that it is used, for example, for statistics. If you want, for example, to fetch statistics every millisecond, you will generate a report, a subscription message, and you will say that every millisecond I want to fetch some data. So every millisecond a timeout occurs. This timeout will call the message handler, which will call the appropriate service model with on indication. The service model will communicate with the RAM, fill the data, encode this data, give back a byte array to the message handler. The message handler will construct an E2AP message, which is an agnostic intermediate representation of the E2AP structs. The E2AP will encode it and it will send it through the endpoint. Now, what happens on the other extreme? Actually, again, a new event happens, so a new packet arrives. So the AP, it will decode this byte array and it will construct an E2AP message, which will be sent to the message handler, which will call the appropriate service model, in this case, on indication. This service model will give back an information element, and the message handler will pass this to the IApps. Now, this may look a bit complicated, but let's repeat it with some code, because we are people. I think that the best is to show the code actually. So this is what it happens in the agent. So when the event type is an indication event, we get the service model, the agent. We call on indication. We generate here the raw data, service model indication data in this example. We generate the indication message with this raw data plus all the other things that the application protocol needs. We encoded it in the AP, in the application protocol, that depends in how we did compile it at the beginning. We get a byte array and we send it through the endpoint. And how does it look this on the rig? Very, very similar. So basically, if there is a network packet, actually, we first get these bits, and we put it in a byte array. We decode it through the AP, and we send it to the message handler, actually. Now, this message handler will call the handle indication rig, which we can find it here. Here is the E2AP message. So the first thing that we do is we extract the information that the service model needs to interpret from this E2AP. So this is done here, service model indication data. We are taking the header, the message, and the call process ID, which are the three information elements for which in an indication message, a service model needs to give the semantic. And we call on indication to the appropriate service model, which will give us the data. Here we assured that we are just doing some statistics for either for the MAC, for the RLC, or for the PDCP, and we publish this information. Maybe you have seen this differ. People that they program in Go, they already know the meaning. For the people that they don't, the basic idea is that when it goes out of a scope, this function will be called. So basically, it's a little trick on the compilers to call what in C++ is called a destructor, so that we don't forget to liberate the memory. So as a summary of what I talk, FlexRig is Oran E2 standards compliant, and we closely follow the standard specification. FlexRig achieves flexibility and extensibility through the service model plugin system. A service model needs to implement the 5 procedures and the 9 information elements for the agent and the rig. And service models are not coupled to encoding and decoding scheme. It's a static polymorphism. It permits changing the scheme smoothly. And you can find more details in a paper that we publish here together at Eurecom. So thank you very much. This was part of the presentation. I think I may move to explain now a bit what you receive in the package, actually, for the service model of the PDCP. And I will answer questions later if there are any. So basically here, if you have opened the zip file of the PDCP service model, you can see here in the service model agent.h that there are the 5 procedures that we mentioned: on subscription, on indication, on control, on E2 setup, and on rig service update. And the extract, it looks like you have the procedures, you have the input and the output for the agent, some free function, you have to free the service model, some allocation functions in case that you allocate some memory, a handle for this share object, actually, the run function ID, and also you give some string for the name. The service model for the rig, which is, these are general for all the service models. It looks very, very similar. You also have on subscription, on indication. On control is a bit tricky because you have 2 request and output. On E2 setup, on rig service update. And again, you have here the free function, allocation, the allocation memory, the handle, an ID, and a string. So what is also common for all of them is how they are interpreted, these 9 information elements: subscription data, indication data, control request data, output data, E2 setup, rig service update. And if you go here to what it has to be done, particularly when you want to define one service model. Well, as I said, there is one function, and it is make PDCP service model agent. There is nothing else. And here you give like an input and output. And the same here applies for the server. There is just one function. Now, of course, the magic goes in the construction of the object. Basically, you create an object which is a bit bigger, actually. You correctly give the function pointers that you need and that they will be called, and you return the base of the object. Basically, we are doing object-oriented approach of inheritance. Here we give the base. As I said before, this encoding and decoding is just a macro, and we define this at compile time, how our encoding and decoding scheme it will be. The agent is very similar. The information elements that you need to give, you have here the 9 of them: the event trigger, the rig action definition, rig action header, the indication message, rig call process, the rig header, outcome, function definition. And the same, this is not here in what you receive, but it should be applied for the flat buffers when you define them. And the same for ASN.1. So the 3 definitions, they should be the same. And here when we encode, we have here these generics. So basically we define, this is a macro, basically encode event trigger. So depending on T, on the type, if it is an PDCP encode plain pointer, we will call this function at compile time. If not, we will call the second one if it is an ASN.1. And I think that you get the idea of how the pointer works here. And for decoding, the idea is the same. So we have here the 9 information elements: event trigger, action definition, indication header, indication message, and the same game for the pointers applies. We also have here like a write and a read. You can check it here. For the read, we did like for indication messages, and for a write, what we implemented basically are the control messages when you are reading and when you are writing. So apart from this, if you are on the package that you received, you can go actually to the test. We always give a test also. So you can open the test. And in this test, we always test our service models before giving them, of course. So what you need to do is you define an input and an output function, in this case, a read agent that you can find here, and write agent. And the idea is that we make the PDCP service model on the agent. We make one on the rig. We create some iterations and we check for the run function ID, the subscription, indication, control. Probably indication, it's worth mentioning it. What we do here is whenever this indication happens, the agent calls on indication. This on indication will indirectly call read agent. In this read agent, the service model is telling the run actually that the type the type of the service model is the PDCP stats version 0, and thus it will call fill PDCP indication data. When it calls here, we create here some randomness so that we also test it with some fuzzy logic, and we are sure that we are at least we know that we are covering more cases or at least many cases than if we are just doing this statically. And we yes, we give value here like randomly to the values. And then what we do is we copy this to an statically defined struct, this case copy. And once it comes back, actually, in the check indication, what we do is we get the bytes that they have been encoded, depending on how you want it to. Then we call on indication on the rig with these bytes. So we convert it again to a struct. And then what we do actually is we compare the two the struct that was before the struct that was on the run, I mean, the one that it was before the agent encoded it, and the struct that it comes out after decoding. And of course, we have to assert that this is true. And if you run, you go to the build, you can maybe make it, you can make it, you can run it, may take a bit. We also run it with code coverage, so we know how good or how bad are our tests. We also profile our code, so we know which functions are fast and which ones are slow. And we use here different sanitizers, the address, the thread, or none. And here the service model encoding can be changed. So this gives us the possibility, for example, of generating some profiling data. So we can come here and we can see that, for example, that check control is taking some time, or fill PDCP indication data is taking us some nanoseconds per call. So we also have an idea where to optimize if we had to. And the same applies here for actually the coverage, so that we can actually know we have also generated coverage data, so we can come here, we can call LCOP, which will give us some results of the coverage, how good were our tests or how bad they were, at least the last ones. We can generate an HTML for this, and we can actually read this on this is an HTML generated file. So here we know how many lines actually they were our code through how many lines actually it went, how many functions they were tried. Keep in mind that we are still like implementing things, and also that some service models, they may not need to implement all of them. So in this case, we should just comment them to get better coverage, but maybe we can go, I don't know, through this encoding. We can see, for example, that the action definition plane is never called, and at least properly here it is said that if the code comes from here, please break and tell me that I'm doing something wrong, that it was not implemented. And the same applies here for call process ID. So given this of the service models, I will go through the next, actually I will set up the environment for the next lab. Actually, here on the left, you can see what we have done here at Eurecom. We have this testbed A, where there is a Quectel 5G module in a Faraday cage, to which we connect a 5G RAN with an B210 USRP. To this machine, actually, in another machine in Venus, here we have a Nokia core network and our Flex rig, and we have here a public IP. And through the E42 application protocol, you from your house, you will be able actually to connect to the base station that it will be running here at Eurecom, and you will actually be able to see some data. So actually, for starting this, let me first start here Wireshark. So that, okay. So the first thing is that we start here the 5G base station in a standalone mode. And as you can see here, E2AP is trying to connect. Okay. Now what we do is we will activate the Quectel module, which is the UE. So here we can see that some data has been. Quectel, it also gave us an IP address. Actually, what we can do is we set up this IP address on bias, and now we can actually pin the UE, so our Quectel 5G UE through a 5G base station. Okay, this is done everything. You are seeing here everything on real time, at least as real as the packets that they travel to your house. And here actually, okay, I will stop here. You can see that the NGAP messages, they were interchanged between the base station and the UE. And okay, so now if we actually run again our Wireshark, okay, we can start our rig. Our rig interchange here some data. And if we stop here, so here we can see actually that what happened is that we started a communication, and here we can see, I don't know if you can see this from your house, but this is an E2AP protocol, and we have here 3 different lengths actually, which indicates the 3 service models that they are here running, that they are MAC stats, RLC stats, and PDCP stats. You can see here actually that the log file, it grows. And you can see here the timestamp, the transmitted packets, and some statistics that, well, my colleagues will explain them like more. They will go more in deep. So I think that now I give the floor to my colleagues, Navid and Hank. Thank you very much.
Thank you very much, Mikel, for this deep dive into FlexRig service model. So I think you also saw our infrastructure. So Mikel, in the meantime, he's trying to solve the issue of the PDCP service model compilation and the testing. So he will come back to you on the chat room. What I want to request to you is that you create your Python environment with the SDK and X app. So let me first start to share my screen. Yeah. So in this lab, the idea of this lab is to demonstrate to you how you can fetch some monitoring information from the live network we are running in the lab. So as I said before, first thing is to download the everything and go to the Lab2 environment, and then you need to have a look at the documentation, markdown documentation, look at the code structure. And I think all of this code structure, we are gonna go through it shortly, and also the installation. So there is a script written in the code whereby you can, and let me actually share with you the environment. Let me just, okay. So you have received these files. Inside here, you have a Lab2 SDK X app, where you have the README, you have the requirement, and you have a setup environment. So there are four structures, four directories that we see here. And yeah, so let me move back here. So please have a look. So we will be shortly running the Hello World live for you. But before that, I want to give very little information about what is this SDK that we are talking, and what is this E42AP protocol that we are defining for FlexRig. So SDK essentially has different blocks. It has an asynchronous interface, which is the communication layer that talks to the rig. It has a data layer that processes the data that is received from the rig. It also stores the context of the XApp. It has an API, and this API is the only interface that the XApp is gonna interact with. And on the right operation, so there is another block, which is the commands that get processed by the command and then sends back to the rig. So this is the structure of the SDK that we developed. Now I want to describe to you the protocol E42AP. So this protocol essentially should cover four action types, including report, insert, control, and policy. This will be essentially the four actions an XApp would like to do on rig. So what we see here on the message sequence chart that we see on the left, the XApp, we see the SDK, and we see the rig. So at the beginning, the XApp starts with the initialization. It runs the init, and this on the level of the SDK shall be triggering the E42 setup request and E42 setup response, which creates the application context at the SDK level, and this provides the XApp ID the capabilities that this rig is capable of providing to this XApp. Let's assume that this XApp wants to get a report. So this is what we actually developed in this version. So it sends a report with a desired service model, for instance, report PDCP. Optionally, it provides a callback functions too. So where this service model is available to report the information, the callback will be called. So this will be translated to E42 subscribe message with the desired SM, and in response we get back the E42 indication data. The data will be processed by the SDK, and based on which the callback function will be called, and the XApp will be informed with the data that is provided by the requested service model. So this process will run periodically until the moment the XApp will remove the report with the SM that have been activated before. This will trigger another E42 messages, and essentially finally the XApp will close the communication channel with the SDK, which will release everything from the rig. So with this, I hand the ball to Hong, which will show you the exact steps that you need to run on your platform. So we go first through the hello world.
Hi everyone, my name is Hưng Nguyễn. I come from the OSA team and the MOSAIC team. And thanks Navid for handing it to me. So the objective of this lab could be introduced for you guys briefly about how to develop the XApp at the moment with by using our SDK. So let's get started with downloading what's the download the package which is already received from I suppose you received from our supporting team. Oops. Give me a second. Oops, I think this might. So for the requirement of this nav is good. You will need to have Python 3 installed in the computer with very stable connections. I recommend to use something like Ethernet or Wi-Fi, so you could be really you can have a very good connection to connect to our setup in testbed. So let's get started with here is a folder that where we're storing the packet I received. So that you guys, let's unzip this file and see what have inside this. Let's go to here, and we go to the NAPS 2, which is M5C. Sorry. So let's just copy it here. Oops. Yeah, here we go. And then just open this one with any of your favorites text editor that you want. And in this case, in my case, I use the Visual Studio Code to either visualize. As you could see here, here's structure that I think Navid already showed you before. We have the data folder which will the structure will be have such at the beginning you have as the data folder contain is will containing the data you save when you run so XR for the moment, and then to the log file which contain the note to help you maybe if you have some problem with debugging, and the source will be contain our SDK, which is you can want to take a look to understanding about SDK work, and finally is the XR. That's we will go through on each of them to help you understand how you can use our SDK to develop the XR. Just to make sure that all of you have this file. If you don't have the link or you cannot get the file, please let us know. I will need you wait for 1 or 2 minutes to make sure that you guys have this. Meanwhile, some of you might want to take a look at the README for the moment. This is our documentation that could be briefly explained for you how you can use this SDK and developing it app at this moment. So let's get back to our screen here. So I suppose now all of you have the package and are ready to for the integration, prepare for environment of this development. So let's get started to install the package, prepare the environments. So first of all, that we will for the sake of simplicity, that get started with creating the virtual environment locally here in this folder. I will call it the MOSAIC5G environment. And we will activate it. Here we are. We go inside the virtual environments, and let's just starting to install the prepare on the necessary package for this SDK by simply running this command p3 install -r and requirements, and then here you go to go. So before I running the Hello One example, let's just go back into the documentations and take a look briefly about structures, and so I can at least introduce how to developing the XR. So for some of you that are familiar with the Python's developments, so this development of this app is very, very simple and similar to the other apps you already developed. This is our design. So before you can set up for the sake of simplicity of this lab, we already let's just ignore this 3.9. It's not easy to set up on the notebook and the SDK environment for use. For this for the XR, actually you needs to import our XApp base from the SDKs, which is a base class for any XApp. If you want to develop for Frederick, this must be the child class of this base class. It will be handle all the necessary the communications between the XApp and Frederick, as you can see from the introduction of Mikan and David on this. To next diving directly into the how you can use. So for the purpose of this app, it's very simple. In this one, we just would like to be establish the connection between the XApp, the Hello World XApp, with the Frederick, and then that simple as that. To just to try the get the feeling of how to develop an XApp here. So for this one with the init functions of the XApp, you also need to be calling the init function for XApp base, and in this way you have to define the Nerf level you want to establish. But I recommend just leave it here, debug at the moment. For the ping timeout, if you remember from the introduction of David about the E42AP protocol, which is have the one of the ping mechanism that could measure the health of connection between the XApp and the Frederick. So the ping here just to tell us after this timeout, we're considering that the connection is closed. If you for the, as you can see here for the conf, it is that the config file is simply just a dictionary, Python dictionary, establish what you want to do with your app, and the configuration specific your app that you want to establish. So here I submit at 3 seconds. So after 3 seconds, if we don't receive any ping byte from the Frederick, considering that the connection is closed. The other option here I recommend to the left there is that for record parameters, just to turn off the recording of the data that you receive from the rigs. And simulation is a mode for run for apply, but you can ignore this one for now. And the file is the one. This one is trigger periodic function is very important. So the way we see how the life cycle of the XApp. So basically that's from our point of view, XApp should have like at first the app should be established connection with Frederick and refers to which service that is want to be supplied, or let's say it's one to REST repositories. For example, service model, for example, like PDCP or MARC or IFC. And then later that we from the XApp, you would like to do something like some customized function whenever the SDK receive the message from Rick, or later you want that after X some kind of periodic time, for example, like every 10 seconds maybe, that you want to do something check back with the data you receive from the 10 second of last n or x second that you want to do. So this parameter is to tell you that do you want to trigger this periodic function or not. If you set it 4, that means that it doesn't do any periodic function for you. So that means that we didn't do anything. So for this Hello one, since we don't need to do anything of this, so I set it as a 4. If you go down in the main, actually it will be very similar for any XApp you receive. Basically here in the conf file, you have some like running time, which I set here at 5 seconds. So basically it means that as first when you launch XApp, the main we will next another thread to handling the atomic correction and do the job for you, and the XApp will live for like shortly 5 seconds and will closing by itself. So actually that's, for example, here, it is a cone running time that you saw before in here. And then after 5 seconds, you will kill. So this is basically all what you have to be done to write very simple header 1 XApp for this moment. So let me try to run it for you to see how it works. So as you can see here, it's informed you that the app already connected to the race, and because we already set up that this app only live for 5 seconds, the app will be closed correctly with the rigs. So that's all you need to be done. So do you have any questions so far, or do you need to can you run successfully with header 1? So without question, I assuming that everything is okay. So let me move on the next XApp, which is a little bit more complex than the, sorry. So far. Okay. Yes, sorry. So actually that's so actually yeah. So maybe I will wait a little bit for everyone, so actually you guys can run the hello ones. If I go with so far, please don't hesitate to stopping me. So let's go with back with the PDCP callback. Maybe it's a little bit more complicated than the header 1 before, but it's based on the header 1. So I will skip more of this and just focusing on what's the differences that you need to adding to make it work. So beside importing the XApp base, which is the one that you see from the header 1 before, maybe we need to add the indicator here. In fact, it's like add-on to let the XApp know which kind of services you want to be get the report. So it could be at the moment we support 3 service model. Like I already mentioned before. So Mark service model, PDCP, and IOC. So let's go slowly. So for this XApp, because the purpose of XApp is that it will be will develop will supply to own the service model that I researched this before, Marks, IOC, and PDCP. But as a PDCP service model, we would like to have some kind of the callback functions, the function that you would like to inspect the stats received from the PDCP SM every time when the SDK receive PDCP matches from Friedrichs. So that is the purpose of this XApp. Very simple. So what is the difference between this one and the one that we have with hello one? So the first difference is that you could see here, like how many interval here you want to call the pairing function which is running on object. At this moment, I'm picking functions, which is do some kind of nice simple statistic. But in fact, let's in this app, we still don't know this pairs yet. So we will see in the next one. So for the Nerf Level, it's the same. Ping timeout is the same. That's the SM. The recall explanation is the same. Trigger periodic function is still false. So that means you still don't launch the periodic function here. But here you will see the differences. The first difference is here. Is that here you inform the SDK that you will want against a report from all the service model identities, MARC, IOC, and PDCP to specify the callback function that you want whenever the SDK receive the PDCP matches. Just put the name of this callback here. So let's see what is it inside this callback. So as you could see here, this function I call it PDCP message handler. So the signature of this callback is very, very simple. So first you have like the name of the functions, and then you have a single parameter that could use for this one. And this parameter is a PDCP messages, which is an instance of this class of PDCP from the data layer. So the interface of PDCP class from data layer. Let me open this one for you so you can see the interface. Very simple. Let's say that here is data layer, and let's look for PDCP class. So PDCP is super simple. It means that here this means that it have a bunch of like attributes that we want to support, and have some JSON to convert this object into JSON for you, just for the convenience. It's super simple. If we go back into here, as you could see that in this PDCP message handler, you have like the, because we don't we do for every 500 PDCP messages that we receive, we start to convert the message received to JSONs, and then this JSON into will show up on screen or and dump into the data folder which I mentioned before here, which we will restore the data that we receive here. So to show up, of course, you can change this one to any logic you want. Here is just okay for you to do it. And then the reason why we pick 500 messages is that because we don't want to have like 1,000 or million thousand of files in this my computer, of course. For the rest, the only change that I changed in here is this for on the main function is only the running time for 30 seconds. So we could have like this example could be live much longer, and you can see the actually effects of the XF for the periodic functions. The red it doesn't change comparing with the hello world. So I may need some minutes for people to rethink this a little bit before I launch. I run this XF. Okay. Yeah. So let me starting to run the XF before we go out of time. So let's see the PDCP callback and see what happened. So as you could see here, that's again we see the connected to the rigs, but here after 10 seconds you start to receive the data. It's for 500 message from PCP, you will receive some informations on screen to show up this one. So you could see that because my connection is not very stable. So very similarly, for the MOSAIC5G, for this MOSAIC5G, it's very similar what you done with PCP, but you just need to train set the MOSAIC message handler for the MOSAIC service to get report, and then the logic is very similar to what from the PCP message handler that we see before. It's much the same. Is that you change from 500 message you want to receive 100. For the rest, it doesn't change. It doesn't change much in this one. So let me running this for you. Okay. So you will see the same thing that you see with PCP XF. Now with data added for every 100. With those data rates much faster than the PCP XF. Yeah, again, we have some connection issues. Yeah, so very quickly, I want to show you the same with IOC. You just need to keep everything the same, only change with ideas with the reports with the code byte for IOC SM with the same logic as the other two except that you have. Yes, so the same output you see as before. We don't change very much. It doesn't change very much on this. So let's go for the last one, which is I think very important for you guys to get much more of this. For this one, we start to introduce the API for this API from SDK. So basically, from this one, you want to subscribe for you want to get a report from all the speech model with different message handler, the same as you see before, which is here. It's very super simple. That you want to be. I want here is to adding the INTI for the characterized local context of XF. I don't think it's very important to do this, so I will go directly to the one interesting here. So the difference here comparing as a XF is that you trigger the pairing functions to do some kind of logic for every some kind of interval here. So actually here this parameter start to make sense that for every 10 seconds you will launch the pairing function, which is you could define around here. So for the API, we have very super simple API to help you to communicate with the context of the SDK. If you're looking back at the README function before, actually the API is very simple. which is you get if for example get attribute function, and then UE you can set up the single UE, the index of UE1 or the list of index of UE1 with a name attribute which is a list of string. For each string could be some kind of one indicator that you want to specify which value or statistic that you want to be interested in. The list of the indicator are listed down here on the left column that you see. So to show up in here for you. So you just need to get this this string for each indicator that you want to interested, and then put it in the API functions, and you will see it back. So let me go back for the monitoring XF. Okay. So here is a list of XF that you want to do. So before we get out of time, I let me run XF so you can see the output of these applications. So as beginning, we don't have any UE corrections. After 10 seconds, you will see start the first periodic function. And here you see the output of the API that we receive. That's the needs of Python with the key inside here. We have dictionary with the key is the indicator that you specific, and the value for the last 3 messages you will receive from PCP or Max storage. And I think that's it is for this now. And I will return back. I think we end my nav here. If you have questions, don't feel free to ask on the chat.
Yeah.
Sorry.
You can maybe go through the chat and see some question about posting the steps to run the hello world from the beginning. It might be a bit fast and someone might be interested to know it.
Okay, thank you, Ang and the team. I think we have 10 minutes left. So let's go with the challenges first. David and Michael.
David, I guess you're mute.
Yes, thank you, Jose, for mentioning this. Yes, so I was just saying that I thank Hong for the steps. I wanted to highlight that the SDK today only supports the report, and we are going to add insert control and policy in the future, near future, very near future. So in this report, we have PDCP, RLC, and MAC. So we have designed the general aspect of this E42 protocol that you see here in my window, and this will also evolve in the near future. So now if we go to the challenge, so we would like you to join us in this journey, and we want together with you go deep in MOSAIC5G. You saw that Michael explained thoroughly how you can design a service model. So if you want to design a new service model, for instance, mobility management, you want to monitor the transmit power control or whatever type of service model you would like to do, you just have the template of the PDCP, and then you can actually develop your own service model, plug it into FlexRig, and then use the SDK framework to develop your XApp. So this is the template we want you to understand here. So the first challenge to this end is to create a service model. So the price for creating the service model is 1K euro. So we would like you to get your hand deep in FlexRig, try to design a service model either for the physical layer or to the RRC layer. And for that, you need to get some understanding on these layers, understand what are the relevant statistics of interest for this service model, and just reuse the PDCP service model and apply it to file with the new statistics, new information that you would like to monitor it through the rig towards the XApp. So the winning solution shall provide a working demo here. So we would like to see it in practice, knowing that FlexRig and SDK, everything will be released before the holidays, and also has no memory leaks, has no undefined behavior, and it is also trade safe. So this would be the price for this one. And the other one is challenge 2, which is easier, and the price is 500 euro. So the first one is related to the PDCP, which stands for computing the throughput and loss rate per UE and per base station for TX and RX, and visualize it over the time. For instance, use it matplot. So you saw that in a get attribute, we could get the relevant attributes of the PDCP that actually help us to calculate the throughput. So here we have the aggregated number of bytes in the TX and RX. We have the timestamp. We could have a window and basically periodically measure the throughput at the PDCP level. Of course, on per UE basis and for total overall base station. On the RLC is the same, RLC throughput. And also what is interesting in RLC is to get the statistics on the retransmission using the metric that we have, which is the number of retransmission bytes at the RLC, that this statistics is available in RLC. And we would like you to compute the median, average, and deviation just for the transmission. So there is no reception, and visualize them over time, again, using, for instance, matplotlib. And on the Mac, also compute the aggregated throughput rate per user for TX and RX, and visualize it over time. So all of this is the statistics already available in related service models for the Mac, RLC, and PDCP. You need to get the specific information. You have the time information, and you can basically calculate these values. The deadline, we will be also put this on the website later, the deadline for the submission of this, but you have some time. So with this, I would like to thank you for joining our workshop here, and we would like you to join us on this journey, starting with these challenges that we presented to you. And if you are interested, please get in touch with us or discover more on the new website that we have created in OpenAir website, OpenAirInterface website. So with that, I pass the ball to Rafael for the closing remarks. And if you have again any questions, please use the chat to so that we can answer your questions. Thank you very much.
Okay, so just for information, I mean, I think Camille will post all the detail on the website on the deadlines and the formality on how to submit your participation on any challenges, not only for MOSAIC5G but also for the RAN and the 5G core that I showed on the previous sessions. I would like to thank all the participants that made these 3 tracks possible. I mean, the University of Utah Powder team, the Northeastern Coliseum team, all the RAN presenters like Laurent, Panos, Fongzi, etc. My team for the 5G core, I mean, Remy, Ismaël, Tin, Rowan, Sagar. I mean, the White Stack team, Sergio and Gabriel, for the nice demonstration they made. Of course, I mean, all the MOSAIC5G team, Navin, Osama, Mikel, Hong, Sofia, Robert, and Alireza that did answer questions. Our strategic partner for their support, all the partners, in fact, and mainly also all the contributors on all the projects, because without contributor, nothing will happen. And you for attending. And last one but not least, I mean, Camille and Irfan for organizing the event. They did a lot of good job. Thank you, Camille. That was a lot of stress for you for your first event to organize. So thanks a lot. I think what I will suggest to MOSAIC5G team is to create a new zip file with instruction for both labs, with the command to execute and maybe the requirement on the operating system for you guys, because I think that will be good tutorials for you guys to participate to the challenges. Okay, once again, thank you very much for attending. It was a very intense 2 days for us. We have an Asian version next week, but I don't think I will attend. But I don't think they will also Zoom. I think it's a live version in Beijing. See you soon. Maybe we will organize webinars also in the meantime towards the next workshop that I hope might be physical next time. We are seeing that for the past 3 workshops now, but let's hope for the better. And enjoy the holiday season. Have a good end of year and see you next year. Bye-bye.